All right, good afternoon. The teaching station is broken yet again, so I can't read Discord, so you'll have to yell at me if anyone comments on it. So yeah, that's great. All right, so again, this is not new content. This is just fun stuff that's kind of related to the course. So I will not test you on Rust or anything like that, but we're going to see a conversion with our bank account. I'm not that good at Rust, so I can't do the conversion on the fly, but we can screw around with it. It's really easy to screw around with. And who here has like used Rust before or even heard of it? We got like a few people. Okay, so we'll quickly go into what it is. This lecture might be a complete crap show because I'm not great at it, so if you want to feel better about yourself for not knowing something, then you can watch me flounder here. But we'll make tons of errors and see what can happen. But basically, Rust is supposed to be billed as a new systems programming language, so it's actually kind of integrated into the Linux kernel now. So new drivers, you can write them in Rust, and it's meant to just be a saner C that has some kind of more C++-like features, but isn't as quite insane as C++ with all its stupid templating and all that kind of stuff. So it also has a few nice goals over C++ where it aims to statically verify some properties of your program so that if you know it compiles, and sometimes you will fight with it to get it to compile, but if you know it compiles and you don't try and get around its rules, then you're guaranteed some nice properties, like you won't have a use after free, so you can't use memory after you free it, which would have saved some of you on Lab 6 that have fixed your own errors. Probably would have saved you on all the other labs while you're developing stuff. You can't double free something, so I can't call free on the same pointer twice. And statically, it verifies that you do not have any data races, which is probably more applicable for you guys because concurrent programming is kind of hard. And there's an unsafe keyword, so it won't let you do a lot of things, especially it doesn't really like you casting pointers and doing all that fun stuff you do in C because it's kind of unsafe. So if you want to tell the compiler, don't worry, I know what I'm doing, there's a keyword called unsafe. You can use it for like a function or a block of code that says, yeah, don't bother me, I know what I'm doing. And the idea behind that is when you inevitably crash your program or something bad happens, well, because the rest of it's verified to be safe, you can just debug looking at your unsafe code. But, oh, I don't know why there's an @ sign there. I accidentally screwed that up. But it only verifies that data races don't happen, but it does not do anything to prevent deadlocks. And trying to get this example not to deadlock was a complete pain in the butt. So we will see that today. So it doesn't completely eliminate some of your problems, but it eliminates a large section of them. So the way it eliminates data races is one of the things it kind of does is keep track of the lifetime of all your variables and how long they last for, and however many times you take references to them. So it also has a keyword called mutable, which you have to declare a variable as mutable if you want to change it, which in other words for us means you want to write to it. So one of the properties it will do is if you have references to something, you are allowed to have as many read-only references as you want because that could not be a data race. But if you have a mutable reference to something, you can only have one. So if you can only have one, we know that even if you have concurrency, that's fine because that is not a data race. Only one, we need 2 concurrent accesses. So let's do this and see how this works. So it should be related to what we did. So the syntax is somewhat nicer and kind of weird. So the main doesn't take any arguments and it doesn't return an integer. It returns a result, and this is a kind of unbelievably nicer way of doing, you know, with the standard C functions, they return -1 and then set error no, and then you have to check it. Well, a result can be one of 2 types. So it's a result and then 2 types. So if it's successful, this is the type it is. And if there's an error or something, it tells you what the type is of the error. And then you can go ahead and handle it and check it without checking if it's -1 or anything. So it's kind of a nice way about this. box is like a safe way for a pointer. Don't have to worry about that. It's basically just to check an argument. So this will go ahead, take all the, this is like the same thing where you use the NV pointer, but it's a bit different in Rust. And we change everything into arguments and just check. Remember, we just take one command line argument that says however many accounts you want to have for our bank simulation, if we remember our bank simulation. And then it has some nice things like you can parse a number straight with that. And these, you'll see in a bunch of Rust code, there's a bunch of question marks. So pretty much every function we know that can fail, like if you're parsing an integer from a string, there's tons of ways for that to fail, right? So in C, if it fails, what happens in C if you use like, what was it, A2I or something like that? What happens if you give it not a number? Anyone have used that before, hopefully? So if you just give it the string like hello and you say convert that to a number, what will it do? I don't know, probably give you like 0 or set error no or do something, but likely, in all likelihood, you've probably never checked the error before. So Rust forces you to check an error. So this parse method, I don't have a good IDE set up for this, but basically returns that same result thing where if it successfully transforms it, it gives you the number that it converted to. Otherwise, it gives you an error. And this question mark thing is kind of a shortcut to say, okay, if it successfully returned, just give me the proper return value. And if it's an error, it'll just abort your program and give you a stack trace and say, hey, it's screwed up at this point. So it kind of does what I've tried to enforce on you guys, like check your errors and just fail out so you actually know what's going on and you don't kind of propagate that error and make it harder to debug. And then we'll just check the number of accounts. So, oh God, so it gets really ugly. So let's skip this for now. Oh, whoops. Sorry. Let me go to the version that does not use threads. So everyone kind of remembers our bank example, right? Where we have a bunch of accounts. And with our bunch of accounts, we just pick a random to one, we pick a random from one, and then we transfer money between them. So anyone want me to revisit that, or does everyone kind of remember the transfer function and what it does? Because we kind of had a question like that before, or yesterday. Monday. Okay, so it took a while to even get this so that the compiler would not complain at me. So this is just getting 2 accounts from an array, and you want mutable reference to them because you want to change the balance because you're trying to transfer from one account to another account. But even getting that to work was a gigantic pain in the butt, and I'll kind of illustrate that here. Let me comment this out first. So where is this? So if you want to define like a vector or just like you can think of a vector as like a dynamic array. This is what you would do. So you would say let is how you declare a variable. So if you want to change the variable after the equal sign, you have to say it's mutable, which is that mute keyword. So it's like let mute test vector, and then you can say vector with capacity. So it's kind of like C++ namespaces. So this is just declaring a vector of size 10. And then the for loops also look a bit different. They don't let you just do I minus minus and screw up the condition or whatever. So they'll have a little shortcut that's just 1 dot dot whatever the other number is. So this for loop will iterate from 1, 2, 3, 4, 5, 6 all the way to 10 and put that value into I. So I just push 10 things onto my vector. So now my vector has 10 things in it, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then if we were in C and wanted to like pass a pointer to another function so that it could change the value of it, which we've seen a few times, you would have to do like, you know, the address of in C to get the address of. Well, it's the same thing in Rust, except if I want to change whatever it's pointing to, I have to say ampersand mute to say, hey, it's mutable, I'm going to change it. So if I do this, I'll say I'll have a reference or essentially a pointer to the 0th element of the list and a pointer to the first element of the list. And then I'm going to modify the 0th element of the list to 2. So in C, that would compile, right? Everything would be good, and it doesn't have any problems with it. But in Rust, if I go ahead and try and build it so it has its own build system, so it will loudly complain at me, and loudly complaining at me. So 1, it's complaining that I don't use the variable element 1. Okay, true, but don't worry about it. And then it says, oh, if this was intentional, it gives you a way to silence the warning by putting a prefix in front of it or silencing it. So it has a lot of ways to kind of communicate with the compiler, which is, there's ways to do this in C, but people generally don't do it. It's also warning me that this variable does not need to be mutable because it's actually a mutable. So this is a pointer to something I can mutate, so I'm not actually changing what I'm pointing to. So this mute keyword, I didn't need to actually use it, so that's it. It tries to limit the amount of mutables you use so that you have like the least amount of chance of writing anything and breaking anything. So we could go ahead and fix that, where essentially it's just a pointer. And the nice thing about this too is those are all variables, but you might notice too that we don't declare the types for them at all. So another nice thing about Rust is it will infer the types for anything. So if you go on to take like a compiler course or like a grad level type system course, you will figure out how it does things like that. It is fairly complicated, but for us, we just get to have the nice benefit of using it. So let's go to our next error. Variable does not need to be mutable. And then this is our error. So it says, cannot borrow test vector as mutable more than once at a time. So does anyone have an idea what in the blue heck it's talking about? Yeah. Sorry?
You have 2 references to the same array, and they're both, you can write to them, but you're only allowed to have one like mutable reference at a time, right?
Yeah, is that what you're going to say too? But so I have 2 references to the array, but technically this is actually okay, right? Because I have 2 references to 2 different spots in the array that do not overlap. So the pointers do not overlap, but they are references within that array. So this is where the thing. So if I did something like this, it would be right, where they're both pointers to the same index. That would definitely be an error where I have 2 mutable references, or you can think of pointers to the same element. But in this case, this should be okay. And if you're used to C, this wouldn't pose any problems, no issues whatsoever. But the annoying thing is this just won't compile because it errs on the side of being conservative. So if you just have one reference to the array, in general, it would need to prove that both the elements are disjoint, and in general, it can't do that. Oh, yeah, was there a question?
Yeah, I was going to ask, like, is the reason based on the fact that, like, technically you could have that, I guess, pointer then point to the next element or something, so it's just, like, prevents you from doing that just in case something could get messed up? Like, it doesn't, like, that's fine, except for, like, the theoretical possibility that it's not, if that makes sense? Like, is there anything, like, inherently problematic with that?
So with what I have now?
Yeah.
No.
Okay.
Yeah.
Can't you like, if it's like stored contiguously, can't you add like 4 bytes and then modify that value?
So pointer arithmetic's unsafe, so it won't let you do that.
Okay.
So you have to like force it to do unsafe, and then if you use unsafe, all bets are off. So like pointer arithmetic and stuff, it doesn't let you do. It strictly discourages you doing that. So this is technically safe, but the compiler is, if you get to compiler courses, it's trying to be really conservative, because in general, it would have to prove that those 2 array elements are disjoint. And in general, that's a very, very hard thing to do. Even though the example given right now, you just have to prove that 0 is not equal to 1. That's pretty simple. but then they'd have to special case a bunch of stuff, then it would work sometime, and it would probably just make your life more of a pain, because the general case is that these could just be two unknown variables, and they come from who knows, and then you have to prove that they don't equal each other, which, yeah, in general is not going to happen. So this is kind of one of the first pain points of this is, at least for you guys, since you know C, hopefully, you guys are technically smarter than the compiler for some things, and the compiler will get in your way, but I'm told eventually you kind of get used to it and it becomes all good. So that was like the first issue, because when we're even doing the serial version of this in Rust, our transfer takes, here, let's go to our transfer. And this is the fixed one. So our transfer takes two accounts, but in Rust, I couldn't just take two, like if I had defined transfer as from taking like a mutable reference to an account, and then two has a mutable reference to an account. Well, the compiler stopped me right there because that's technically the same array, and then it would say, hey, you know, you can't have two mutable references to the same array, so it won't let you do that. So you might notice some other crap on here. One thing you recognize, so everyone should recognize Mutex, and the other thing is an arc. Anyone have any idea what the hell an arc is? So how many of you have actually like used C++ for things? One? Okay. So basically arcs are pointers, and it keeps track of like the number of pointers to a thing, but it keeps track of how many pointers there are to it. So it's kind of like our inodes, how it keeps track of how many things point to it. An arc does essentially the same thing, but for pointers. And a pointer, if you want to be like nice in Java, generally if a pointer actually points to something valid, you call it a reference and not a pointer. So an arc is basically just a reference, a pointer that keeps track of how many things point to it, and the A stands for atomic, so it's an atomic pointer. So when it adjusts the number of things that point to something, it does it atomically, so it's nice and thread safe and everything. So that way we can have multiple pointers to our array and keep track of it that way, and you have to like wrap types in Rust. It's kind of annoying, but once you figure it out, it's not too bad. So let's go here. So yeah, this is kind of what our, so this is what our transfer function looks like. So it fixes a bunch of issues that we had before where we had rand that was really, really slow because it shared state. But here, if you have a random number generator or RNG, well, you have to declare it as kind of a variable, which is kind of like an object, and then it has its own state, so it's nice and thread safe. And then this is where we go through the number of transfers. So we come up with a random index to the, for the from account, random index from the to account, and then this is how we create multiple pointers to it. So instead, this is what you would normally do to access an element of an array, but because we're not allowed to take multiple references to an array, these are actually pointers, and .clone on the pointer just makes another copy of the pointer, so it's your own pointer, and it increments that number, that count that's actually referring to it. So you can actually keep track of the number of references to something, and that's again how to make things safe, and that you don't have to call free on it. So this keeps track of how many things point to something. It's the same thing as inode, so as soon as you have no references to that memory, whenever it goes to 0, then it would free the memory for you. You don't have to worry about it. There's no extra onus on you to know when to free. It just frees whenever there's no references. So this will take 2 pointers, count them, give them to transfer. And in transfer, this is our thread safe one. But it basically just does the same thing where we just take 10% from the from account, take it from the to account, and that's it. So any questions about that? So yeah, sorry, it's a bit of a mess because I had to put in the solution because, yeah, I can't remember how to do this again. Like, look at the type on this thing. It's gross. Some of it might be because I have no idea what the hell I'm doing, but hey, it works. Okay, so let's see the thread safe version. Oops, not that one. So for the thread safe version, or the one with threads, well, you can create an array of threads in a vector, which is just like a dynamically sized array. And then we would take a pointer to the whole array. So this is what this represents. So you give each thread a pointer to the array. And then this is, instead of pthread run, it's called thread spawn. And there's this move keyword. So any arguments you give, you can't use them after you give them away. So if I tried to use accounts clone here, this would give you an error because it would say, hey, so one of the other things it does, it has a concept called ownership. So it will keep track of who owns what variable so that and it ensures that you only have one owner for each variable. So like if it was some dynamically allocated memory, you're the only owner of it. So if you make it to the end, you can call free on it and no one else uses it. So you're fine, you're free to free it. There'll be no free after use or anything like that. All right, any questions about that? So we basically have to give a pointer to the whole accounts array for each individual thread that's all counted. And the reason for that is because Rust, or you in the general case, don't know how long a thread lasts and don't know how long the main function lasts and don't know, if the main lasts longer than the threads or the threads last longer than main in general. So it makes sure that you transfer it there so that you can always use that vector array because it won't actually free the memory associated with that array until there's no more references to it. So you're always safe to use it. You'll never have a use after free because you never even call free. It only calls free itself whenever there's no references to it. But it's also a bit silly in this case because we know we have a bunch of threads and we join them. So this is the way to join them. And unwrap is just to check for errors again and just get the value of it. Otherwise, it just kind of dies. So we know that our array actually lives longer than all the threads, but unfortunately, Rest is not quite as smart as us, but we'll live with it. All right, any questions for this? Okay, so let's go in here. So this was more of a pain to get right. So for all the locks, so by default, you are not allowed to try and modify anything or even read multiple accounts at the same time because it can't argue that that's a safe thing to do. So you're only allowed to actually change values if they're protected by a mutex. And the way in Rust to use a mutex is it's kind of like a type qualifier around an account. So if I want to modify the account or get at any data associated with the account, I have to go through the mutex first. So the only way it will make sure that the only way I can even try and modify the account is if I already have a lock and acquire lock. So in Rust, the from is actually a lock. The arc is just a pointer. It'll get rid of the pointer for you. So you can think of the from account as just being a mutex around an account. So instead of doing pthread, mutex, lock, or whatever, you do a lock on the mutex, and then unwrap would check for errors. So check error node, do all that stuff, and then just crash the program if something bad happens. And then after that, our lock is acquired, and we can actually modify the from account. So if we do something, let's do my initial solution. So all right. So if we do this and we, whoops, wrong build system. All right. So if we do this and we run it, do we have any data races? So I'll move up some code. So it acquires both the locks, and then here it modifies the accounts. So do I have any data races here? Hopefully not, because I have a lock, like right after this, I've acquired the lock I've acquired the lock to 2, and it will, a nice thing about 2 is Rust will automatically unlock them when the function's done, so you don't have to worry about calling unlock. So at this point, I have both the locks, and they'll both be unlocked whenever it reaches the end of the function. So I don't have any data races. What problem do I have, though? Deadlocks. So Rust doesn't prevent deadlocks, so let's go ahead and see if I try and do run. So if I try and run it, this might be the first thing you promised about a lot about Rust, but if I try and run it, well, I'm screwed because I have a deadlock and there's nothing I can do about it. So does anyone remember the 2 easy ways to avoid doing a deadlock? Yeah.
You can always maintain the same order.
Yeah. Okay, yeah. First one is, hey, if I always maintain the same order, I won't have a deadlock. Doing that in Rust is, as far as I can tell, impossible. So, because here, it depends what order too. So the account does have an ID that's unique, but there's kind of a catch-22 here. If I even want to read the ID, because it's declared like this, even if I want to access anything about the account, even to read it, I have to acquire the mutex, and I've already deadlocked myself at that point, right? I can't do anything about it, or I can't like change the lines or do anything, or if you can actually check the pointers and do it based off the pointers, but you can only acquire the locks in the right order, and then you forget which account's associated with what lock. And the only way I could think to actually fix that is actually writing 2 transfer functions depending on the order of them. But that seemed super lame and kind of a buzzkill. So anyone remember the second solution? Yeah.
You finish transferring one first and then the other?
While having both locks.
With only having one.
Yeah, let's assume I want both locks, though, at the same time. So I could do the same thing as in the exam where I just kind of, so unlike the exam, this gets a bit different because it takes a percentage of an account. So if you like have a partial transfer, it gets kind of weird that you probably don't expect that. So what about if I want to maintain 2 locks? So one was always acquire them in the same order. What was the other deadlock or another deadlock condition? Yeah.
Do you have to like try lock instead?
Yeah, try lock, because one of the conditions is hold and wait, right? One thread has a lock while it's trying to get another one. So if I can break that condition, then I don't have the possibility of a deadlock. So that's what essentially I came up with to do, and it works the same in Rust, but kind of looks a bit different. So you can, it has like weird things where the thing at the equal sign can be an expression. So you can say a variable is equal to a loop. As long as it eventually gets to a variable, Rust is okay with that, and the scope is only within the scope of that, which is kind of cool. So in the loop, I do a try lock to the 2. So at this point, I would have already acquired from. So I do a try lock, and then it's that result type. So you use a let expression, it does pattern matching. So a proper result is called OK. So if it's OK, that means I acquired the lock, and then I just have a break that says return that variable, assign to account to account, so it actually represents the locked mutex. Otherwise, there's drop from account, which if we wrote this in C, this would be mutex unlock, but drop is the Rust keyword for kind of any variable that as soon as it goes out of scope, drop's automatically called on it. So if this was like a malloc thing, drop would call free. In the case of mutexes, drop calls unlock. So it's just kind of a more generic term that represents a whole bunch of stuff. So this drop from account is the same as unlock from account. And then I have a yield, and then I would try and acquire the from lock again, which is what we had before. And then we go ahead and we just try it over and over again. So if I have this, hey, it should hopefully prevent a deadlock, and yay, it works. So that's Rust. It's kind of nice. I thought you guys should see it, even though it might not have made that much sense, but it probably needs to, it's probably a good thing to know. If you start writing concurrent code, it will in some cases make your life a lot easier. All right, so any questions about that? If not, let's talk about the exam, yay. Okay, so we can start doing more review. I'll take up more questions, and then the plan for Thursday is to finish whatever we didn't do today, or please ask other questions so I have something to do. Otherwise, it defaults to open office hours, and I'll just stand there and wait for questions. Whoops, dog. Okay, so this question says, hey, given 4 threads, you want to 4 threads that are properly created, set up to run. You want to ensure some ordering between them. So ordering should immediately trigger you to think of semaphores. So that's a nice way to ensure order. You could also use condition variables, but generally if you can, semaphores are the easier thing to do. And I guess there is a question, I mean, I gave you the front page to the exam, and there's a question called semaphores. So probably shouldn't be a question what you actually have to use. So this says, this was a closed book exam, so I had to tell them what post and wait did. But for you guys, you have an open book or at least a cheat sheet, so I won't tell you. So you should know how semaphores work, but pretty easy. They have an increment, decrement. Decrement will make sure it won't go negative. If it's 0, it just waits until it gets incremented by something else, and then it would eventually decrement it. So we have 4 threads. They each call their own thread function, and there's some comments between all the functions, and you want to ensure the order between them. So thread 1 runs F1, then F2, and then in thread 2, it only runs F3, and we want to ensure an order that, hey, F1 only runs after F3 only runs after F1 completes, F4 only runs after F1 completes, and then in thread 4, we have F5 that should only run after F2 completes, and then F6 that should only run after F3 and F4 complete. So let's work on this. So first constraint is probably this one we want to work on. So anyone have any ideas how I would make this work? How I would make sure that F3 only runs after F1 is done? Oh, yep.
Try to decrement from thread 2.
So thread 2, you want so we want to wait. So we'll start off with a wait. We'll just use sema 1 or something. That's the first semaphore. So we'll set it off to wait first. So everyone agree with that? Everyone like that? Okay. So next thing you need to think of a semaphore probably is what should the initial value of it be? So what should the initial value of that semaphore 1 be? 7. Everyone likes 7? Yeah, thumbs up. All right. So what will 7 do? Yeah. 0, no? Yeah. People like 0 better? Okay, we like 0 better. So, whoa, geez. No one saw that. All right, let's just use that 0 then. Yeah. So we can probably use 0. So 0 makes it so that, hey, because we don't know the order between any of the threads executing, it'll make sure that if thread 2 executed before thread 1, for whatever reason, that it would hit the wait. If the initial value was anything other than 0, it would just pass it immediately. So if it was 7, it would just go from 7 to 6, and then it would call F3, and it just called F3 before F1 happened. So that would be bad. So this looks good so far, but we have still another issue. So in this case, will it ever call F3? No, right? So nothing posts, so we should probably work on the other part of it. So where should we place the post? Yeah. After F1. Okay, so we can post. All right, everyone agree with that? So that looks like that handles that constraint. So now, if thread 2 runs first, it would hit the wait. The value of the semaphore is 0. Can't do anything. So it would have to wait until eventually the only way to post it is for thread 1 to start executing, finish F1, and then it would post it. It would go from 0 to 1. Then thread 2 at its leisure could go from 1 to 0, then call F3. So it can only happen after after F1 gets called. So everyone good with that? All right. What about F4? So let's tackle this one. So that's that constraint fixed. What about this constraint? So it's the same thing. So, yeah.
We should wait on stem 1 before calling F4, and then after F1 we should actually post twice.
Yeah, so we just do the same thing again. So we'll wait. So now if thread 3 gets called first, well, the initial value is 0. Can't do anything, has to wait for a post. So if we leave it as is, well, thread 1 will execute sometime, execute F1, and then increment that from a 1 to a 0. And then either thread 1 or thread 2 would pass this wait and go from 1 to 0. And then the other one would be stuck there forever. So we still need that sem post sem1. So now a whole bunch of different orderings that can happen, but that constraint still works. So if thread 2 tries to execute, couldn't do anything. Thread 3 tries to execute, can't do anything, and it would wait for thread 1 to go finish F1. Maybe it only posts once, and then another one of thread 2 or 3 executes, and then it passes by. Then eventually it will make it back to thread 1, and it would go from 0 to 1 again, and then the other one could pass by. Or it could just do the 2 posts in a row, go from 0 all the way to 2. Either way works. Doesn't matter, our constraint's still good. All right, so we like that. So hey, we can give her, so check, check. What about F5? So this is only runs after F2 completes, which is this guy here. So how am I going to do that? Yep.
You start by posting after F2, and then wait on, like you use a different semaphore, so it would be like at sem2.
Okay, so use a different semaphore.
And then you can wait after, you can wait before F5.
All right, new semaphore. All right, everyone like the direction that's heading in? What did we forget to do? Yeah, we forgot to initialize it. What should its value probably be? 0, right? If it's anything other than 0, then thread 4 could go ahead, execute thread 5, and then we're screwed. So this looks good, and we used another semaphore. So would it work if I reuse semaphore 1 for that? No, because it actually needs to be a different one because you're not actually sure. Although technically you could, so there is a sillier solution because you guys are being really, really good and, you know, making sure that the other threads can start as soon as possible. But I could actually reduce the number of semaphores I use, and the alternate solution is I could make this semaphore 1 and it could still work. Anyone guess what else I would have to change for that to still work while technically still being true? Yeah.
You can post after, I think, thread 2.
Post after thread 2?
Post after F3.
Post after F3, like here? So that wouldn't quite work. Whoa. Okay, whatever, we leave that. So what you could do is you could move the, okay, so I want to erase things so it doesn't screw up. But you could move these posts to be after F2 as well, so that all the other threads can't run until thread 1's done. And technically, all the conditions are still true. But this solution is actually better because it allows the threads to run as soon as possible. And there's a sub-question that asks what can run in parallel at the same time. So if you gave that solution, you essentially make sure nothing can run at the same time as thread 1, which is pretty lame. So you guys are doing the smarter thing. But that was just an aside. Okay, so this is sem2. All right, so we're done with that condition. We just got the last one left. So F6 only runs after F3 and F4 complete. Any ideas how I would do that? Yep.
Wait, can you initialize it to negative?
Nope. Yeah, semaphores, you're not allowed to initialize to negative. They have to be unsigned, so it's 0 up. Yep.
You can post sem3 after F3 and F4, and then wait on sem3 twice before F6.
Yeah, okay, so we could go ahead, post a new semaphore, sem3, we could call it. Only after, once after F4, and again after F3. Oh, it's already there. Well, so we could post sem3, and then here we need 2 waits. I'll move the ampersand, sem wait. So that way, it has to wait for both of them to be done before actually executing F6, right? So if only one's done, it would make it past one wait, not the other, so it needs actually both of them. So any questions about that one? Cool. So last part was just for each function state, what functions could run in parallel with it not including itself, write none if it can only run by itself. So it's just kind of looking at it, looking at the dependencies and seeing what could run in parallel at the same time if you had enough CPU cores. So I can leave that one and we can gloss over the rest of them just to let me know on Discord what you actually want me to cover more in depth tomorrow or any other topics you want me to cover since you have the front page. So for the last 5 minutes, let's just go through it quick. So memory allocation was buddy allocator. Should know what that is. That only allocates in size powers of 2. And here I set it so it needs to be able to handle 8 allocations of 10 bytes each. So this is just knowing that, hey, if they're 10 bytes, if I have a buddy allocator, it'd be 16 bytes. So how big does my memory block need to be? Well, it would need to be 8 times 16, which is 128, and then just asked about fragmentation. Disks, so this was just, remember all those RAID configurations? It essentially just asks, oh, you know, I have a bunch of hard drives, what's my usable space, how many drives can fail? Just pretty much that lecture in a nutshell. File system, so this is making sure that even though you didn't write a CP, you know what LN means. So this is like using your knowledge to explain the difference between hard links and copying in terms of inodes and blocks. Assume you have a file that's called my file that contains 2,000 whatever bytes. Block size is 4 kilobytes, so it fits on a single block. As a hint, I said I ran the commands for you and you find the output below. And the hint here was that, hey, if I do a hard link to my file, the inodes are the same because they're hard links, so it refers to the same thing. But if I do a CP, like a copy, and create a file, that there's a new inode. So if there's a new inode, that inode also has its own data blocks. So they're completely independent, and the copying would be, it would create, as part of the copy, it would create a new inode for the copy file, then go in and copy the contents of all the blocks and make an exact copy of it and make sure that the new inode it just created points to those. So that's how files normally work if you copy a file, right? If I copy a file and then I modify the original one, it doesn't affect the copy of the file I made. Nothing changes. While if I had a hard link, they both actually refer to the same data. So if I change a hard link through like my file and then look at LN file after, the changes are in both of those. They're not actually copies of each other. They're actually pointing to the same thing. Then, yeah, last one was just virtual machines. Just general questions about virtual machines. Are they a good idea? What's their benefit? So this is kind of more like, these sub-questions are more like your short answer questions. So your short answer question would be like either 8A or 8B. So this is kind of what your short answer questions look like. So there's no big virtual machines question, but you can probably guess wow, I talked too much. But yeah, I probably made a question about it. So, and it probably looks like one of these. But obviously won't ask you the same thing because that's kind of lame. All right, so any other questions, concerns, or whatever for the last and final lecture? Yep.
Just as an aside, for the previous question, when you run the cp command, couldn't you have some sort of copy on write mechanism instead of copying the whole thing?
Yeah, so, yeah. So you could have copy on write on this, but it would behave like you have copy on write on memory, right? If you have copy on write on memory, as far as you're concerned, it's an actual copy, like it behaves like an actual copy. You were just way more clever about it. But even if this could use copy on write, right? You just wouldn't know about it, just like virtual memory uses copy on write and you have no idea. It still looks like a copy. But if it needs to make, you know, it just delays doing the copying to the latest possible period. All right, yeah, any other questions, concerns, or whatever? Probably should have written down what I did because that was probably a dead giveaway. God, I really need to just shut up. All right, well, on that note, pulling for you. We're all in this together.